Okay, so the next part of this question is basically the fifth part, or part D, is part D of the fifth part of exercise 1. Of exercise 1. and the set is that we have is basically the set A of human beings. The set A of human beings in a town in a particular time and the relation that we have on A is basically R is equal to all the ordered pairs x comma y, such that x is wife of y. X is wife of y. Okay, so there's actually a problem here. I think what they mean by this, when basically there is a relation in human beings, there is some sort of relationship in human beings called wife and husband. But there is also a relationship in human being called wife and wife. And there is also a relationship in the human being which is called husband and husband. Meaning that these days, well, there is basically two women can get married legally as well. Two men can get married legally as well. So these two types of relationships do also exist. But then if you want to solve this problem, we'll have to agree on one of these. And since this is the classical standard relationship of wife and husband, we will basically concentrate on this one. So what that means is that then you have the set A of human beings in a town in a given time, and R is basically all the ordered pairs x comma y, such that x is the wife of y. And so since we have agreed on the first option that we talked about, if x is the wife of y, y automatically becomes the husband of x, right? So which means that now if you want to know if R is reflexive, then of course you know that x comma x x comma x does not belong to R, because x cannot be her own wife. That's based on that relationship is not possible. Which means that basically R is not reflexive. R is not reflexive. If you want to know whether R is symmetric, then the condition that we used for being symmetric was that if basically A1 comma A2 belonging to R implies that implies that A2 comma A1 also belongs to R for all basically A1 and A2 belonging to A, right? Now let's suppose that basically let's assume that some x1 y1 belongs to basically A, which is this set here, which means that basically based on this, x is the wife of y, which means that x1 is the wife of y1. x1 is the wife of y1, and which means that basically then if x1 is the wife of y1, that means that y1 is the husband of x1, which means that basically y1 and comma x1 does not belong to R, which means that basically R is not symmetric, right? R is not symmetric, so R is not reflexive. Indeed, if X is the wife of Y, Y is the husband of X, so R is not transitive. So let me see, there is a couple of things written here. So basically R is not symmetric. Now to check whether R is basically transitive, you need to check if this basically condition is true, which is A1 comma A2 belonging to R and A2 comma A3 belonging to R. That implies that A1 comma A3 belongs to R for all A1, A2 and A3 belonging to A, right? Now let's suppose that, for example, let's assume that some x1 comma y1 belongs to R, which means that, and also let's assume that some y1 comma y2 belongs to R, so belongs to R, which means that x1 is the wife of y1 and y1 is the wife of y2, y2. So if x1 is the wife of y1, and y1 is the wife of y2, so you have x1, y1 and y2 here. x1 is the wife of y1, y1 is the wife of so that means that this is a man and x1 is the wife of this man, and y1 is supposed to be again the wife of y2, which is not possible, because if x1 is supposed to be the wife of y1, then y1 is supposed to be a man. But then if y1 is supposed to be the wife of y2, then y1 is supposed to be a woman, and so y1 cannot be a man and a woman at the same time. So which means that basically this situation is not possible. which is not possible. Therefore, R is not basically transitive, right? Now, the next part of this question is part E of this question. So this is part E of the fifth part of exercise 1, which is, again, we have the set of A of human beings in a town in a particular time. And the R and the relation defined on this set is basically R is equal to all the ordered pairs x comma y, such that x is father of y. X is the father of y. Okay. Now, in order to find out whether R is reflexive, well, x comma x, that means that basically x is the father of himself. That doesn't belong to R. Because x cannot be the father of himself. The father of himself. X cannot be the father of himself, right? And therefore, R is not reflexive. Now, if you want to know whether R is symmetric, let's assume that some x1 comma y1 belongs to A, for example, which means that x1 is the father of y1, and that means that basically y1 is the son of x1, which means that basically y1 comma x1 cannot belong to R, right? So if you could prove that y1 is also the father of x1, then y1 comma x1 would belong to R. Otherwise, you cannot say that y1 comma x1 belongs to R. Which means that basically R is not symmetric. Now, to prove that, basically, to see whether basically R is transitive, you can, let's assume that basically some x comma y belongs to R, and some y comma z also belongs to R, which means that X is the father of Y. X is the father of Y, and also Y is the father of Z. So if X is the father of Y, then Y becomes the son of X, and then if Y is the father of Z, then Z becomes the son of Y. So X becomes the grandfather of Z. Which means that X comma Z does not belong to R. Does not belong to R. So if X comma Y and Y comma Z belong to R, then X comma Z does not belong to R, which means that R is not transitive. In order for X comma Z to belong to R, X has to be also the father of Z, which is not the case. So X comma Z does not belong to R. Okay, so that was basically question number 1. Now question number 2 is this question here, and we have actually quite a lot of questions here, around 16 questions here. But these questions have to be done so that the concept is understood. You cannot, you cannot really skip these questions. You have to solve all of these questions, because this concept is, any concept, if it has to be understood, it has to be done through solving problems. Question number 2, or exercise 2, you want to show that the relation R in the set R of real numbers defined as R is equal to A comma B such that A is less than or equal to B squared is neither reflexive nor symmetric nor transitive. Let me see if we have enough space here. I think, okay, so I don't really know how much space I'm going to need, but that's fine. You want to show that the relation R in the set R of real numbers defined as R is equal to basically the order set A comma B such that A is less than or equal to B squared is neither reflexive nor symmetric nor transitive. Okay, so first of all, basically about this question, if you want to check whether basically R is reflexive, if R is reflexive, then you need to show that A comma A you need to show that A comma A belongs to R for all A belonging to A, right? Which is not possible because suppose that A comma B suppose that A comma B belongs to R. Suppose that A comma B belongs to R, right? Now in this situation, if A can be equal to B, then you can say that basically A comma B is equal to basically A comma A, for example, which means that basically R is reflexive. Which means that R is reflexive. But the problem is that A cannot be equal to B, since if A comma B belongs to R, that means that basically A is less than or equal to B squared. So there are two cases here. Case 1 means that A is equal to B squared, and case 2 you can say that basically basically A is less than B squared. A is less than B squared. And in this case basically A is not equal to B, and in this case A is not equal to B, of course. So that means that then this never happens, and then R is never reflexive, which means that basically R is not reflexive. On the other hand, to show the same thing, basically to show that R is not reflexive, you can say that it can be observed. It can be observed that for example 1/2 comma 1/2 cannot belong to R, because over here we are saying that A is less than or equal to B squared, right? A is less than or equal to B squared, meaning that this ordered pair has to satisfy this equation or this inequality, meaning that basically 1/2, taking this 1/2 for A, is less than or equal to basically 1/2 squared, and 1/2 is, that means that 1/2 is less than or equal to 1/4. So here I'm saying that 1/2 is either equal to or less than 1/4, which is not true. Therefore, this doesn't belong to R. Therefore, 1/2 comma 1/2 cannot belong to R. And so you can say that basically R is not reflexive. R is not reflexive. So we said that R is not reflexive. Now let's see if we can show that it's not symmetric. In order to show that R is not symmetric, so symmetric means that suppose that there is some, basically we said that the condition was that a is less than or equal to b squared, meaning that if I take some a and b, let's say that, for example, b squared is equal to, let's take b as square root of 9. Let's take b as square root of 9. And let's take then the square root of 9 whole square is equal to 9, and a has to be less than or equal to, let's take that as 5. Right? So now let's imagine that some x comma y belongs to R. Let's suppose that some x comma y belongs to R, which implies that basically a is less than or equal to b squared, right? Or which implies that basically x is less than or equal to y squared. X is less than or equal to y squared, right? Now, so what you can say here is that if y comma x has to belong to R, basically y has to be less than or equal to x squared, right? Y has to be less than or equal to x squared, which cannot be because one tells us that basically, let's call this number 2. It tells us that 2 cannot be the case based on our assumption. Right? Which means that, so basically you can say that y comma x does not belong to R, which means that basically R is not symmetric. R is not symmetric. Now, another way of saying the same thing, is that you can say that 1 comma 4 belongs to R. 1 comma 4 belongs to R because basically you have x is less than or equal to y squared, which is of course the case here. The condition is x is less than or equal to y squared. There is no problem with the condition here, having this in mind. So x1 is less than or equal to basically 4 squared, which is equal to 16. There is no problem there. So 1 comma 4 belongs to R. But 4 is not less than or equal to 1, right? Or 1 squared, basically 1 squared, right? That means that 4 comma 1 does not belong to R, right? And so you can say that R is not symmetric. R is not symmetric. That's another way of saying the same thing. Now, the next part of this problem is it's not easy to get basically the counter example to show that R is not transitive. Meaning that normally what you would do is that you would assume that, for example, some x comma y belongs to R, and some y comma z also belongs to R, which implies that x is less than or equal to y squared and y is less than or equal to z squared. And then based on that, you need to decide whether basically x is less than or equal to z squared, right? If that is the case, then basically you can say that x comma z belongs to R. Otherwise not, right? Now basically it's not exactly very easy to decide that, because you see that you're dealing with these two inequalities, x is less than or equal to y squared and y is less than or equal to z squared, and you want to find some sort of inequality between x and z, which is exactly not very easy to get. Meaning that you know that x is less than or equal to, so these are of course not no intervals, these are some points on some number line, meaning that, for example, you can say that basically if you say that x is less than or equal to y squared, there has been some y, and then y squared is then some point on the number line, and of course you know that y could have been some negative value or some positive value, and then when you raise it to the second power, it becomes a positive value. It becomes some positive value here, and x could be some negative or positive value, any number, any real number really. And then again, the same thing applies to y and z squared as well. So this is not very easy to decide. I mean, I did search my whole brain in order to get to this, to get to some way to find some relationship between x and z, right? Meaning that what you would do is normally using algebra. I don't think that I have the basically the sufficient tools to decide that. Meaning that if x is less than or equal to y squared and y is less than or equal to z squared, right? So then, in order to get some inequality between x and z, and just forget about y squared, then you would have to basically raise this to the second power. Raise this to the second power. For example, y squared is less than or equal to z squared, right? And then over here you have x is less than or equal to y squared, and well, here y squared is here y squared is basically, here x is less than or equal to y squared, and here y squared is, you can argue that basically y squared is greater than or equal to x and less than or equal to z squared. So since that is the case, then you can say that z squared is less than or equal to x. when you know that basically y squared is greater than or equal to x. Y squared is greater than or equal to x, and y squared is less than or equal to z squared. If y squared is greater than or equal to x, that means that it's some value, well, greater than or equal to x, and it's some value less than or equal to z squared. Meaning that if I have some number line, for example, over here, and if I take any value over here as y squared, it is greater than or equal to x, meaning that x has to be to the left of y squared. I'm sorry, y squared has to be some value to the right of x. X should be somewhere over here, or at most over here, right? And basically, when we say that y squared is less than or equal to z squared, that means that z squared is some value over here, or at least somewhere over here. That means that x is less than or equal to z squared. This is not correct. This is not correct. So x is less than or equal to, means that x is less than or equal to z squared, right? Now, if x is less than or equal to z squared, then what we want to show here, if x is basically what was the case here? So over here we have a is less than or equal to b squared, right? We want to show if x is less than or equal to z squared. We want to show if x is less than or equal to z squared. Well, using this logic, it seems that that is the case, but there must be something wrong with the logic that I'm using here, because I have actually seen a counter example in the solutions that does negate my solution, meaning that you can simply say that forgetting about all of the logic that I used here, you can simply say that basically 3, 2, so 3, 2 and 2, 1.5 do belong to R, because R, the rule that we use for R is that x is less than or equal to y squared. Over here you can see that 3 is less than or equal to 4, and 2 is less than or equal to 2.25, right? So both of these do belong to R. But if you write 3, 1.5, that there you have 3 less than or equal to 2.25, which is not true. Which is not true, right? So what that means is that basically 3, that means that 3, 1.5 does not belong to R, although 3.2 and 2, although 3, 2 and 2, 1.5 do belong to R, which means that basically R is not transitive. R is not transitive. Okay. So that was question number 2. We will discuss the rest of these in the next video. I'll see you in the next video.